Boolean algebra is the foundation of digital logic design, and it's fascinating how it simplifies complex logic into manageable equations. At its core, Boolean algebra uses just two values, true and false, often represented as 1 and 0. This binary system is the bedrock of all digital circuits. Now, let's dive into logic gates. These are the building blocks of digital circuits, each performing a specific logical function. The gate outputs true only when all its inputs are true. Think of it as a strict bouncer at a club. Everyone must be on the guest list for entry. The OR gate, on the other hand, is more lenient. It outputs true if at least one input is true. Picture it as a party where you can get in if you know just one of the hosts. Then we have a NOT gate, which is a bit of contrarian. It flips the input. If you give it a true value, it returns false and vice versa. This negation is crucial for creating more complex circuits. Combining these gates allows us to create intricate logic functions. And this is where things get really interesting. Moving on to combinational logic blocks, we start with adders. Adders are essential for performing arithmetic operations in digital systems. The simplest form, the half adder, takes two binary digits and adds them, producing a sum and a carry output. When you need to add more than 2 bits, you use a full adder, which can handle carry inputs from previous additions. This is how computers perform calculations at lightning speed. Next up are multiplexers, or muxes for short. These clever devices select one input from multiple sources based on a set of control signals. Imagine you're at a restaurant with a menu of options, and you can only choose one dish at a time. The multiplexer acts like the waiter, taking your selection and sending it to the kitchen. This selection process is vital in data routing and communication systems. Now let's talk about encoders. An encoder takes multiple input lines and converts them into a binary code on the output lines. It's like a translator, turning various languages into a common tone. For instance, if you have 8 input lines, the encoder will produce a 3-bit binary output that represents which input is active. This is essential for efficiently managing data in digital systems. On the flip side, we have decoders. Decoders do the opposite of encoders. They take binary input and activate one specific output line corresponding to that input. Think of it as a light switch panel where each switch corresponds to a different light. When you flip a switch, only one light turns on, illuminating the corresponding output. Visual aids like diagrams and truth tables are invaluable for understanding these concepts. Truth tables lay out all possible input combinations and their corresponding outputs, making it easier to visualize how each logic gate and block functions. Diagrams help illustrate the connections and flow of signals, reinforcing the concepts we've discussed. In summary, Boolean algebra, logic gates, and combinational logic blocks like adders, multiplexers, encoders, and decoders form the backbone of digital electronics. They enable computers to perform complex calculations, manage data, and execute commands efficiently. Understanding these principles not only enhances our grasp of technology, but also empowers us to innovate in the digital age.